Good morning, good afternoon, and good evening. I'm Tom Concolino, and I'm here with our presenter, Keisuke Saito. Thank you all for attending Rigaku's webinar. And this is the third episode of our Practical XRD series, of our XRD with Confidence series. And today we're focusing on thin films and choosing the right measurement for structure, strain, and thickness. Now, please note that if you missed any of our previous webinars, you can view them on the Rigaku website. So this is going to be an interactive session, and I'll be posting relevant links in the chat window. We'll be taking your questions live during the webcast and answering them during the session, so please don't wait until the end to ask. And please submit those questions via the Q&A button at the bottom of your screen. We won't be monitoring the raised hand function, and we'll try to answer as many questions as we can during the webinar, and we'll respond to any unanswered questions after the session is complete. If, for whatever reason, you have difficulty viewing the webinar live, please note that it is being recorded and you will be able to view the recording beginning tomorrow. And with that said, I'll turn it over to Keisuke.
All right, thank you, Tom. So welcome to this episode. So today I'm going to discuss a thin film characterization by X-ray diffraction. So first, I focus on polycrystalline thin film analysis on the first three topics. And the last three topics, I'm going to switch the talk over to high-resolution X-ray diffraction. So let's get started. So preferred orientation of crystals. So let me discuss how the preferred orientations could be introduced to your thin film. So if your film is epitaxial growth thin film, so your film is deposited on top of the single crystal substrate, and your layer grown on a single crystal substrate with succeeding crystal structure from the substrate. If you spatter or deposit your film on amorphous or largely mismatched substrate, in this case, the lattice planes with the lowest surface energy will orient parallel to the sample surface. For example, if your layer has a body-centered cubic structure, so the 110 atomic plane has the lowest surface energy. If your sample is face-centered cubic structure, so the 111 atomic plane has the lowest surface energy. So in the last episodes, so we learned as a powder diffraction. So if your sample is like a powder form, so your crystal doesn't have any preferred orientation. So if so you can scan any direction to your sample surface, so then you get all the necessary peaks to identify your crystal. However, so once the preferred orientation is introduced, so depending on which direction you scan, sometimes you see strong peak, sometimes you see very weak peak. So by the way, those are the X-ray diffraction image taken by the photograph. If your sample is epitaxial or a single crystal, the situation is even worse, because now your diffraction is not dividing anymore, but your sample shows like a spot, like a dots. So now you need to carefully align your sample to diffractometer, otherwise you may not get any signal from your sample. So this example is showing copper. So assuming copper is powder now. So the circle shows the grain. So powder, like I said, so your grain is randomly oriented. So from the powder scan or thin film scan, you get all the necessary peaks. So you identify the copper as a phase. However, if you deposit copper as a thin film on the glass substrate, for example, because this is face-centered cubic structure, so the 111 atomic plane is going to align parallel to the sample surface. So eventually you see only 111 or its higher order diffraction peak. So only from one or two peaks, it's almost impossible to identify the phase. So that's a challenge to analyze the thin film by X-ray diffraction. So now I'm going to discuss about XRD scans for polycrystalline thin films. What kind of scans so we do normally? The first scan always like a symmetric 2 theta theta scan. So this is the same as powder diffraction. However, the difference is optics. So I hope you see here, after the X-ray source, we have optics, which is called X-ray mirror. So X-ray mirror converts the divergent beam from the source to the parallel beam. For thin film, we need to have parallel beam. So then X-ray hits a sample with incident angle theta, and the detector is placed at the same angle from the sample surface with scattering or diffraction angle 2 theta here. So then we scan source and detector at the same speed. In such a case, scattering vector is perpendicular from the surface. So we are seeing these spacings on the diffractogram, which is parallel to the sample perpendicular direction. So that means, so we analyze preferred orientation phase information perpendicular from the sample surface. But this geometry, there is one big disadvantage for thin film, which is penetration of the X-ray. So X-ray penetrates very, very deep. So that's why majority of the information comes from substrate or thicker layer. If you're interested in thin layer, so the thin layer diffraction peak is hidden by the majority of the information from the substrate. So if so we may need to switch over to grazing-incidence X-ray diffraction geometry. So one of the grazing-incidence scan is in-plane scan. So now the X-ray from the source or optics hit the sample with very shallow incident angle, typically less than 1 degree. So then X-ray hits the atomic plane, which is perpendicular from the sample surface with incident angle phi, and the detector angle is 2 theta chi in this example, and we scan phi and the 2 theta chi together. So then in this case, the scattering vector k is almost parallel to the sample surface. So with this geometry, so we are analyzing these spacings parallel to the sample surface. So preferred orientation phase information to that direction are analyzed. So by changing the incident angle here, so you may be able to see depth profile of the phase or preferred orientation. So that's a benefit of the grazing-incidence scan. This movie is showing how we achieve the in-plane scan. As you see, the detector is rotating parallel to the sample surface, and the sample is spinning in plane. But this in-plane geometry requires a specific option on your diffractometer. If your diffractometer does not equip with this option, so one of the alternative way to do the grazing-incidence scan is grazing-incidence XRD. Sometimes it's called as a GID, for example. So this is out of plane scan, so which means the detector is scanning out of the plane. However, the incident angle here is kept very shallow, like an in-plane scan. So that's why this is still like a grazing-incidence diffraction. With the traditional, like a PSA parallel solar analyzer, so you place the solar analyzer in front of the detector to resolve the 2 theta angle here. The other option might be 1D fast GID scan. So this was newly developed. So I just put the link to our YouTube movie video. So this provides you much more intensity because the detector is scanned by 1D mode. Diffracted beams once focused on the receiving slit. So this provides intensity. But in this case, the detector is going to be 1D, so which means much faster. All right. But in either case, so the scattering vector k is tilted from the sample perpendicular direction. So we are looking at this spacing from the tilted direction, but the problem is this tilt angle depends on the 2 theta. So it means every different 2 theta angle peak has different tilt angle. So that makes analysis very, very difficult. So that's why we normally limit this GID method to the thin film, which does not have strong preferred orientation.
Hello, everyone.
Hello?
Sorry, that was something popped up on my computer.
That's okay.
My apologies.
All right. So let's see the diffractometer. So X-ray source from the on the left-hand side. So X-ray is from here, and X-ray hits the sample. This is your sample, and detector on the right-hand side. So X-ray mirror is sitting right after the X-ray source, as we discussed. So this converts the divergent beam to the parallel beam. Your sample is sitting on top of the so-called chi-phi cradle. So this cradle provides you two motion of the freedom. So one is a tilt, which is chi-axis, and the phi is a rotation in plane. So then 1D or 2D detector records a diffractogram. And the in-plane axis is sitting below the sample surface. So this is the second goniometer rotates a detector parallel to the sample surface. So the 2D detector, or could be 1D detector, let's say it's a multi-dimensional detector, is getting very popular on the lab-based diffractometer recently. So this example is showing a hybrid pixel array detector. This doesn't require attenuator, so means this detector can measure direct beam from the source without any attenuation. And each pixel has a resolution about 0.02 degree, which is good enough for most of the thin film sample. And lastly, the detector covers almost 30-degree to theta range by single shot. So this accelerates your reciprocal space mapping, for example, much faster compared to the traditional point detector.
Okay, so Keisuke, we did have a couple questions come in already.
Sure.
So let's get to those. The first one is when to choose in-plane versus grazing incidence versus, let's say, standard grazing incidence, right? So if you can maybe dive into that. I think you talked about that a little bit later, but again, good.
Yeah, very good question. Thank you.
Good first question.
Yeah, very good question. Thank you very much. So the GID, as I discussed, GID can be only applicable, right, to the film without any preferred orientation. So if your sample doesn't have any preferred orientation, you can apply both in-plane GID. But if your sample shows preferred orientation, so then in-plane scan is the only option for the grazing-incidence scan.
Okay. Okay, thank you. And then second question, and I think we can get this one in real quick, is do you need that in-plane arm to do in-plane scans?
Yes and no. To control the penetration depth, so we have to have the dedicated goniometer to rotate the detectors parallel to the sample surface. However, if you don't care about the penetration depth of the X-ray, so if you don't have an in-plane arm, so simply you can tilt your sample almost 90 degree. So then you can do conventional theta to theta scan, like a powder scan. Intensity is going to be low, but still you can do the in-plane scan.
Okay. All right, let's move on. We've got a polling question for everyone. So let me get that launched. And as everybody can see, it's what type of films do you typically analyze? And so the answers are epitaxial and polycrystalline. And we're getting a pretty good mix of answers here, Keisuke, so far. About half of you have answered, and a lot of you do both. A lot of you do polycrystalline, and many of you just do epitaxial. So we're seeing a good mix of users here. Give the poll another 10, 15 seconds here.
Okay, perfect. All right, thank you so much.
Let me go ahead and end it here. And so again, yeah, we're looking at 50% of our users or of our listeners that responded here do polycrystalline, and then another 40% do both, Keisuke. So and then 10% are only doing epitaxial film, which is also quite a good number.
Okay,
So,
perfect.
Oops, I'm sorry. I didn't share the results with our users. So let me do that real quick so everybody can actually see the answer. And please, we'll continue on. Thanks, Keisuke.
All right, thank you. Okay, thank you, everybody. So let me continue. So let me discuss one example. So how I analyzed, in this case, iron oxide with the 5-nanometer thick film by using X-ray diffraction. So this is a sample structure, and the sample is shown on the right top corner by picture. So topmost surface, so this was my interest layer, iron oxide, only 5-nanometer thick. As you may know, the iron oxide has a lot of polymorphs. So polymorph means a similar chemical concentration, composition, but different crystal structure. For example, the wurtzite, hematite, maghemite, magnetite, right? Those are made from iron and oxygen, but different crystal structure. So the purpose of this investigation was to know what kind of the crystal phase so we grow on top of the substrate. Underlying layer copper oxide, so we knew this is tenorite phase, but thickness is 4 times thicker compared to iron oxide. So this suggests me the majority of the information, if I do powder scan, majority of the information comes from copper oxide, not iron oxide. So that was my challenge. Titanium was adhesive layer, which was amorphous. So I didn't expect any signal from the titanium. Substrate silicon 001. All right, so symmetric 2 theta theta scan. So this is what I got. Sharp peak, number 1, and the broad peaks. As you may know, the peak width, right, broad or sharp, so corresponds to the crystallite size through the Scherrer equation. So this is the first thing I did. So peak number 2 and 4, the peak width was about 0.9 degree, which is corresponding to crystallite size about 11 nanometer. While peak number 3 and 5, so those are a little broader compared to second and the fourth peaks, which was about 1.9, which corresponds to 5 nanometer crystallite size. What is a Scherrer equation? So most of us may know already. So D, crystallite size, K lambda divided by beta. So this is a peak broadening, and cosine Bragg angle theta. For thin film, because it's typically oriented, and also typically the shape of the crystallite or grain is not really sphere, especially when the oriented film, the shape factor should be 1.0. For powder, or if you check AI or Google, right? So the people typically use 0.9, but this is assumption, right? This assumes your crystallite is a spherical shape and randomly oriented. And beta, also we have 2 different definitions. So most of the diffraction pattern looks like a Gaussian. In this case, so the peak broadening should be calculated by this formula. And this is your measured peak width, needs to be subtracted, right? The instrument broadening. So how do we know the instrument broadening? So you simply measure some of the standard, for example, the NIST provided standard reference powder materials like lanthanum hexabrite, silicon powder. That's perfectly fine. So I calculated. So assuming instrument broadening, in this case, 0.2 degree, so this is caused by diffractometer itself, and 2 theta 40 degree. So this is the peak from the iron oxide, and the sample broadening beta m. So this was a parameter horizontal direction, and the crystallite size vertical direction. As you see here, the sharper peak, like a smaller beta, provides larger crystallite size, while the broader peak provides a smaller crystallite size. And more importantly, for the thin film in general, so this is a range of the crystallite size you may be able to analyze. So normally I say between 1 nanometer up to 100 nanometer. So it depends on 2 theta, many different conditions, but in general, so this is a measurable range. How about a sharp peak? If you are familiar with a silicon substrate, I'm pretty sure sometimes uses this peak, right? So the 2 theta are around 33 degree. But silicon, if this is silicon peak, this should be 002, but 002 is a forbidden diffraction, so it means 0 intensity. So Dr. Zamzile, so he's one of the smart lab users. So he published this paper back in 2014. So he discussed this peak, and his conclusion was this is not actually silicon 200, but was a so-called multiple diffraction. So the multiple diffraction is like this. This is very schematic, but the incoming beam from the left is diffracted more than 1 time by different HK lattice planes and going out to the symmetric diffraction condition. So to identify that, so you place your silicon wafer and you fix the diffractometer 33 to theta, half of that, and you rotate your sample along the phi direction. So then you should be able to see such a peaks, right? The stronger peak is from twice diffracted by 113 silicon lattice planes, and the smaller peak here was diffracted by 315 and 115 silicon planes, right? So then if you place a phi to the highest peak, for example here, so you see this peak, but if you drive the phi to the angle where you don't see any peak, so then this peak disappears. So this is how you can align your silicon crystal, especially, so that you don't see this sharp peak around 33 degrees. All right, so let's go back. So 2 theta theta scan, let's do phase identification. Like I said, the penetration is deep, so that's why majority of the peak came from copper oxide. So 2 blue dots are from the tenorite phase. So those are the XRD database pattern. So those 2 are from the copper oxide. How about iron oxide? So the iron oxide could be, this peak is overlap to the tenorite, but this broad peak is specifically from the iron oxide. This could be magnetite, magnetite. How about the other phases? Hematite. So hematite should show the highest peak around this purple area. I didn't see it. So most probably we don't have any hematite. And the wurtzite has the highest peak here in the red area. So this might be overlapped with the magnetite peak here because this peak is so broad. So the question here is, can we only probe the surface layer? Yes, we can. But if you do so we need to think about how we do this. So probing the surface layers only with the X-ray, so we need to control the penetration. The penetration depth D around the X-ray critical angle total refraction, theta C, is calculated by this very simple formula, right? X-ray wavelength, pi, and large B. So large B is a function of the instant angle X-ray omega and the refractive index, delta and beta. So delta and beta are material dependent, also X-ray energy dependent parameter. So it means as long as you know the energy of X-ray your materials, you should be able to calculate. So then the critical angle total refraction theta C is calculated through the square root of the 2 times of the delta, again, refractive index. So assuming this, so this is the calculated result. So I calculated for magnetite iron 2 oxygen 3 because this is the topmost surface. And the critical angle total refraction was 0.32 degrees. And I hope you see here, below the critical angle total refraction, penetration depth, the vertical direction is limited, this nanometer scale, only a couple of nanometers. So this is the area we need to focus on. So if you control the instant angle of X-ray in this area, so you might be able to limit the penetration only down to iron oxide layer. So this is the result. So I did in-plane scan, not a GID, with a fixed omega angle 0.32. This is exactly the critical angle total refraction. So that's why I had very small copper oxide peaks, but still I saw the copper oxide peaks, but very small. So then majority of the other peaks are iron oxide peaks. The first of all, magnetite, magnetite. So those 2 always very similar. Unfortunately, we cannot distinguish between, especially when it's grown as a thin film because signal is very low. How about wurtzite? Wurtzite, the purple, might be, again, so this peak is overlapped with the magnetite. It's quite difficult to say if we have wurtzite or not. But what I found is beta iron oxide. This is a metastable phase for iron oxygen system. And this was never found by the outer plane scan. So especially the first peak around the 23 or 24 degrees. So this shows iron oxide, beta iron oxide phase on this sample. How about the peak width? The same Scherrer equation for copper oxide. So we found 11 nanometer, which is identical as what we found from the outer plane scan. And the iron oxide, 4 nanometer, about the same as the number we found from the theta to theta outer plane scan. So that means, so the copper oxide has a 20 nanometer. The thickness is consisting of 2 crystallite sides, while iron oxide consists only 1 crystallite through the thickness. And also the sizes are the same, in plane direction, outer plane direction, which suggests the crystallite size is uniform from the in-plane direction to the outer plane direction. So GID scan, so I did GID because I found there was no preferred orientation, right? Like we discussed, one of the question. And, but this time I changed the instant angle from 0.2 to 0.35. and the penetration calculation on the right-hand side. So when the incident angle was high, like a 0.3 or 0.35, so penetration more than 10 nanometer, let's say, right? So the purple, 0.3, 0.35, orange or yellow, right? So means the copper oxygen is excited. So many peaks corresponding to copper oxide, tenorite. However, if you put the incident angle shallower than the critical angle total refraction, so now I saw only the broad peaks, for example, this peak, this peak, this peak, which is corresponding to iron oxide, right? For example, magnetite, magnehemite, right? So those two peaks. And the first peak, like an in-plane scan, so this is from the beta iron oxide. So let me summarize my talk. So 2 theta theta scan, like a powder scan. So this is the autoplane scan. So you get surface normal perpendicular information only, which is not sensitive to the thin layers, but should be done first. So sometimes, we try to start from in-plane scan. I do not recommend doing that. Let's start from theta to theta scan. So in-plane XRD, which is sensitive to the surface layers, you may be able to see the depth profiling. Grazing-incidence scan the same as in-plane, but this is only applicable on the non-textured the thin films.
Okay, so we've had a few good questions come in. A couple of them actually are they're the same. So going back to the Scherrer equation case, okay, you mentioned the beta of the in that equation, and so we had two questions come in of how do you determine the beta of the instrument, or how do you calculate the measurement? So I think it's one slide, couple slides
this
right
one.
there. That beta, yes.
Okay, very good. So that's a good question. Thank you very much. So first of all, the beta instrument, so you can run some of the standard materials like NIST. This is National Institute of Standard and Technology, right, in the United States. And you can buy the standard powder from them, and silicon LAB6 lanthanum hexabolide, and you can measure those powders with the same configuration. So this is the instrument of broadening. So then beta measured, this is FWHM. This is full width half maximum. So means assuming the profile is like a Gaussian profile. So we define the peak width as a 50% intensity level from the peak top. So this is the FWHM. And of course, this should be radian, not a degree. So you need to convert degree to radian, and you put those information to this equation.
Okay. All right. And then we had a couple of questions actually about the 2D detectors. And so one is, does the pixel resolution mean that you can't confidently differentiate peaks at, say, x of 0 and x of 0.01 or 0.001, essentially? So can you truly differentiate the two theta angles?
Okay, very good question. Actually, very good question. Thank you. XRD profile, right? So you see on the screen, right, on the diffractometer is a convolution between every broadening caused by everything. For example, X-ray source, optics, slit, sample, and detector. So the detector resolution is one of the resolution convoluted in the profile. So that means, so even though the pixel resolution is 0.02, it doesn't guarantee, so you can separate the 0.02 degree separated peaks, because if the X-ray is more, incident X-ray is more divergent than the 0.02, so the peak is broadened by the incident beam, not by the detector. So that's why it's difficult to answer to your question. It's not a straightforward, but it's a mixture between every contributions.
Okay. All right. Very good. All right. Let's move on to the polling question. Make sure we get you to be able to finish your presentation. Okay, okay.
That's a good idea. Yeah.
All right. So I'm going to launch polling question number 2 while you're bringing that up on your screen. And it's do you run in plane scans or GIXRD scans? And the answers can be yes to GI, yes to in plane, both or neither. And interestingly, KSK, everybody does a lot of everything. So here we'll let a few more answers come in here. We've got about 40% of the people have answered so far, and
but many of them neither. So I hope this
Yes.
webinar series help you to identify which methods should be applied to your thin films.
Exactly. And I think some of the questions that we'll end up taking later on, I'm seeing that there's some good questions here. So let's give this another couple of seconds here, and then I'll end the poll. We've got about, more than half have answered now. So let me end that poll, and let's share the results for all to see. So interestingly, right, GIXRD, we're seeing a 30%, both 30%, neither a little more than 30%, and in plane only at 6%. So this is quite an eclectic group we have here, Keisuke.
Understood. All right. Thank you so much.
Film people and some powder people. Thank you very much.
Okay.
Thanks.
Understood. Thanks, Tom, and everybody. All right. So let me continue then. So next topic, let's switch to high resolution X-ray diffraction. This is mainly applied to epitaxial thin film. So first, so let me discuss diffraction measurement types and the instrument configurations. Symmetric 2 theta omega scan right now, not theta anymore, because omega could be different from half of the 2 theta. So we call incident angle as a omega, not a theta, especially in this HRXRD field. So, but the scan itself is the same, but only difference is here. So for HRXRD, so we need to monochromate X-ray down to K alpha 1. So to do so, we have to have an instant monochromator here. So the square box, so those are single crystal germanium. X-ray is 2 times diffracted by the 2 single crystal germanium. So then introduced to the sample. So the information for this scan is the same, perpendicular direction, but epitaxial people, I don't know if this is the proper English or not, but the people who is working on epitaxial films. So typically people say peak separation between layer peak, substrate peak as a lattice mismatch, right? So I will discuss why later on. So then some of the epifilms may show the thickness fringes or satellite peaks from the multi-layers, from the repeated structure. So if you see it, so you may be able to determine the thickness from the fringes or satellite peaks. So once you figure out surface perpendicular direction, so you can continue doing omega scan. So omega scan, you change only omega. So you scan tube and the detector like this. So this provides you, right, mosaicity. So mosaicity means by introducing the dislocation due to the lattice mismatch, mainly between the substrate and the layer, dislocations are introduced at the interface. So then, because of that, the growth direction of the crystal deviates. So through the rocking curve, so you can analyze that through the peak width of the rocking curve. So then people continue reciprocal space mapping, typically. What's a reciprocal space mapping? So we do omega scan. Typically, we see tilted direction. So that's why scattering vector K is tilted a little bit. So we do omega scan. 1D or 2D detector covers a certain range along the 2 theta. And this is how we record. So I will discuss a little bit more details later. So from this measurement, so you can know that these spacings of the layer crystal, both the perpendicular direction and the in-plane direction. And so you can discuss stress and the relaxation between the substrate and the layer. So before going to the RSM details, so let me discuss about the monochromator. So we have 2-bounce monochromator and the 4-bounce monochromator. Of course, there are pros and cons. So 2-bounce provides higher intensity, but larger dispersion. A 4-bounce monochromator, smaller dispersion, but low intensity, right? Always. Everything is not perfect, right? All right, so then let me show you. So this is a dispersion diagram or resolution versus Bragg angle, horizontal direction. So 2-bounce, red and pink, you see, like a hockey stick shape, right? Like a V shape. So that means the resolution really depends on the Bragg angle, while 4-bounce monochromator provides you stable, like a constant resolution over the wide Bragg angle range. Intensity also different. So relative intensity scale here. So 2-bounce monochromators provide more intensity compared to 4-bounce. And those are the typical application. For 2-to-2-bounce, we normally apply to gallium nitride, zinc oxide, carbide, and epitaxial metal oxide films. 402 bounds, typically we apply for compound semiconductors like a silicon gallium arsenide, indium phosphide, these kind of things. 4 bounds, this is only when you need constant resolution over the wide to theta range. Intensity is very small compared to 2 bounces. And sometimes you may need to have triple axis. If you're familiar with XRD, sometimes you hear this kind of terminology, right? Triple axis, what is this? So triple axis, we put additional channel cut germanium crystal on the receiving side. So this improves to theta resolution down to 0.003, which is very high resolution. However, this resolution is a little too much to align the sample. For single crystal, like I discussed at the very beginning of the slide, you need to align your crystal. Otherwise, you don't get anything. But for this alignment, so you need to have poor resolution. So to do so this is just an example from us. So this device, yellow highlighted box on the left-hand side, switches slit configuration, analyzer configuration by applying delta to theta offset, so you can switch between freely. So this kind of setup is necessary because the first we need to use a slit configuration to align your crystal. So then just before the scan, so you put the analyzer crystal like this. So why do we need this? So analyzer crystal suppresses the peak broadening caused by the mosaicity. So that means, so if your film is expected to have a large mosaicity, for example, gallium nitride, in this example, like a gallium nitride quantum well structure, indium gallium nitride, 4 times repetition on the gallium nitride substrate, a lot of mosaicity. This is 20 years ago sample, and then comparison slit and the analyzer crystal, the same sample. So totally different resolution, right? So that is the reason why we may need to have analyzer crystal. But if your sample is perfect, smaller mismatch system, so then you don't need it. So analyzer just kills intensity. So just slit configuration is enough.
Okay, so we are to our final polling question here, and then Keisuke will work his way through the rest of his slides. And so the question is, who has performed a symmetric scan, a rocking curve, or reciprocal space measurements? And this is multiple choice, so please go ahead and click all of them if you've done all of them, and we'll let this roll for a little bit here while we get some answers.
Oh, very good number.
Symmetric scans, a lot of symmetric scans, a lot of rocking curve, actually. This is very good.
Okay, right. Shall we share the result?
Yeah, let's go ahead. We've had about half of the participants here, and since again, Keisuke's got 12 to 15 minutes left to finish up, I want to make sure that we have time for him to go through his presentation. So as you can see, of the 50% roughly that answered, almost all of them have done a symmetric scan at minimum, and then roughly half have done a rocking curve or reciprocal space map as well. So that's actually a very good set of polls. So with that, we will end the polling, and you can go ahead and continue. Thank you, Keisuke.
All right, thank you very much. I was surprised. 40% of the folks here are doing reciprocal space mapping, right? It's good.
That's really good. That is very good.
All right, so let me continue. So let me discuss high resolution diffraction scans in the reciprocal space. To understand the RSM result, we need to understand the reciprocal space. So first, the reciprocal lattice point. So reciprocal lattice point is calculated by this formula. So I hope everybody knows, right? So G vector, this is a reciprocal lattice vector, HKL, this is Miller indices, right? It's calculated by HKL, Miller indices, multiplied with, for example, this is A star, means a reciprocal unit cell in the reciprocal space, right? A star, B star, C star, and A star, B star, C star calculated by this. But point is, the size of the G, HKL, is inverse of the D. So that's the point. And assuming some cubic crystal, right? Lattice parameter A and C. So horizontal direction A-axis, perpendicular direction C-axis. What is a unit cell in the reciprocal space? You just simply need to calculate the inverse, right? So inverse of the C-axis lattice parameter A-axis. So this is a unit cell parameter in the reciprocal space. So then you simply overlay, spread over the reciprocal lattice space. So this is the reciprocal lattice point. For example, then every intersections has a H-scale indices, like a 100 along the A-axis direction, 200, 3, 4, 5, 6, along the C direction, 1, 2, 3, 4, right? So intersection between A and C, for example, 101, 202, 303. So this is very simple, right? So this is how you can write the reciprocal lattice point in the reciprocal space. But the question is this: so how do we measure this reciprocal lattice point, right? So I try to connect between the reciprocal lattice and X-ray diffraction. So Bragg equation, everybody knows. 2D sine theta equals lambda, right? So X-ray hits a sample with theta, scattering angle to theta, right? So now we introduce wave vector. So wave vector is a reciprocal wavelength of the X-ray, right? So the size of the wave vector is inverse of the lambda. So we introduce that. So if you replace a lambda in the Bragg equation with a k, so the Bragg equation can be written by this: 2 times of the k sine theta equals to inverse of the d. So what is a k, 2k sine theta? So now, so I just translated this kd parallel to here, right? Because this is the vector and the vector. So the ki here, so this is the incoming X-ray wave vector, kd diffracted wave vector here. So 2k sine theta. So this is a 2k k sine theta is actually here, right? Because this is a Bragg angle theta. So this is a k. K sine theta is here. So 2 times is actually the green. So the size of the green vector is actually the 2k sine theta. And the Bragg equation is telling us, so this green is the same as the inverse of the D space. So this is the Bragg equation in the reciprocal space. And so 2k sine theta, also this green vector, is a subtraction between the two vectors between kd and ki, right? So this is kd and ki. So this subtraction is starting from here up to the end of the kd vector. So means the size of the green is inverse of the d, but simultaneously this equals to the kd minus ki. So that's a point. So we introduce momentum transfer scattering vector k. Actually, the kd minus ki is a momentum transfer or scattering vector. So large k vector is calculated by kd minus ki. So the point is, X-ray diffractometer. So we are monitoring the intensity at the end of the k vector. So we are looking at here at the diffractometer. So to see that 004 diffraction in this example, so simply we need to drive this k to the top of the red dot, 004 diffraction. That's it. So it means the k vector should be aligned to the g vector, which is a reciprocal lattice vector. This is how we measure the reciprocal lattice point, right? Like this. So it was like that. So we align the k to the g. So then you get this signal. All right. So then if you know this, so it's very simple, which scan, scanning to which direction. For example, omega scan. So we fix the 2 theta here, right? So we only rotate the omega here. So it means this triangle rotates. So it means the scattering vector large K rotates along the divisorial ring. So the orange vector, so this is a scanning direction in omega scan. So this is called rocking curve, right? So then other scan, like a 2 theta theta scan, right? So we change the theta and 2 theta at the speed 1 to 2. So then this purple vector is elongated along the radial direction, but this is perpendicular from the sample surface. So this scan is called radial scan, especially by XRD people, right? Like me, for example. All right, what about 2 theta omega scan? Omega could be different from half of the Bragg angle. Half of the 2 theta, which means Bragg angle theta. So that's why you can tilt the scattering vector. If you do 2 theta omega scan, again, the purple vector is moving along the radial direction, but tilted direction. So that's the difference between 2 theta theta and 2 theta omega. To measure the reciprocal space map, so we combine those scanning, like a 2 theta omega scan, radial scan. If you scan only 2 theta, right, so this is the scanning direction. And if you scan omega, so this is the scanning direction. So you combine 2 scan axes out of the 3 scan conditions which is presented here. For example, 2 theta omega scan omega offset. So either way is fine, but the purpose is to map out the intensity distribution over some certain area in the reciprocal space to see this diffraction spot. So this is the reciprocal space mapping. All right, so how do we interpret? So assuming we measure 204, so now the a-axis 100 direction parallel to the qx, which means in plane direction, out of plane 001 c-axis direction. So by knowing the qx, qz, so the qx corresponds to the 200d spacing, and the qz is proportional to the inverse of the d004. So by that, so you can calculate in-plane, out-of-plane lattice parameters from the single reciprocal space mapping result. So let me discuss one example today, epitaxial perovskite thin films. So I try to define the structure and the thickness of this film. So this is a sample. By the way, this sample was provided by Professor Dr. Matza, Los Alamos National Lab, and Dr. Browning, Oak Ridge National Lab. Thank you so much. This sample had substrate LSAT, lanthanum strontium aluminate tantalate. This is a cubic structure. This is a lattice parameter. And the 45 nanometer thick L5BO layer on top of the substrate. So what is the L5BO? So this is perovskite, and the A side L, so lanthanum, and the B side are 5 different transition metals like chromium, manganese, iron, cobalt, nickel. In this example, same ratio between the 5 elements here. But the question is, depending on the concentration, so the crystal structure is different. For example, chromium, manganese, iron, orthorhombic, cobalt, nickel, rhombohedral. So my question was, so what is the actual crystal structure of this L5BO? So that was the purpose. So again, so let's start from surface perpendicular to theta theta scan. So I had incident monochromator, and 00L direction was scanned, 001 diffraction, 2, 3, 4, 2 theta is getting higher, around 22, 46, 73, and 105, right? So 0012 and partially 3, not only the layer diffraction peak, right, like this, but also we saw very beautiful thickness fringes like this. So that's why let's focus on 001. So this is 001. So first of all, from the peak separation, substrate peak, right, on the right-hand side, and the layer peak on the left-hand side, so we can calculate so-called lattice mismatch. So lattice mismatch is how much out-of-plane lattice parameter differs compared to substrate. So this is a lattice mismatch. And delta C over C, right? So calculated by C lattice parameter layer minus substrate normalized by substrate lattice parameter. Simple. And you put the Bragg equation. So then you can have the Bragg angle information here. Theta S, this is Bragg angle for substrate. This is a layer. And after the calculation, I found, so this system, from this peak separation, mismatch was 0.00471 or 0.471%. So this is a size difference of the lattice constant of the layer compared to substrate. From this mismatch, right, so the layer lattice parameter CL is calculated by this equation, very simple, and we found the layer lattice parameter 0.3887. So you can know this from the surface perpendicular direction. What about thickness? The thickness is calculated from the different equation, of course. So thickness T, lambda, Bragg angle sine twice of the Bragg angle, and the delta theta is a space between the fringe in the radian, not a degree. So then I found 44.2 nanometer thick. This is the film thickness. All right. So by the way, the peak separation between layer and the substrate, right? So we found, so this is a mismatch. So how the mismatch changes depending on the Bragg angle. So you can tell from the first derivative of the Bragg equation. So this is the first derivative of the Bragg equation, delta d over d minus cotangent theta delta theta. So this is the peak separation, right? And this is actually the mismatch. And if you calculate peak separation, now I multiplied by 2, because normally the horizontal scale is 2 theta, right? So delta 2 theta, peak separation minus 2 times of the tangent theta, this is a mismatch. So we found this is 0.0047. So putting those numbers into this first derivative formula of the Bragg equation. So this is showing how much is the peak separation between layer and the substrate depending on the 2 theta angle. So as you see, if you go to lower angle, peak separation goes smaller. If you go to high angle peak, separation gets larger. So this red bar is showing the peak separation so that you can see both on this graph. So compared to 003, 004 provides you much more peak separation. So this suggests if you are struggling separating closely separated two peaks, so better to go to higher 2 theta side so that you can separate much better compared to lower index or lower 2 theta diffraction peak. Let's go back. Reciprocal space mapping. This is 004, surface perpendicular direction, substrate 1 layer peak here. So I measured 204. This is tilted direction, right? So then I found 2 layer peaks, right? Not 1, 2. The other side, 204 plus. So plus means higher incident angle, minus typically shallower incident angle compared to the exit angle here. So plus side, again, the 2 spot. So the question is, how do we interpret, right? So this result. So this was my interpretation. So from the those 3 spot, right, has the same QZ, the same height. So this is suggesting this crystal, right, that showed those peaks are like a tetragonal, like this. And the QZ provided this lattice parameter along the C direction, and distance between this and that provided in plane, in this case, a B-axis lattice constant. How about the other spot? For example, the orange spot, 204 minus here, is actually from this tilted crystal structure. This is monoclinic. So the beta angle is not 90 degree, 0.5 degree tilted. Why 0.5? You can just simply calculate the angle here. So this was 0.5 degree. So 98.5. And distance between this and that provided 0.387 nanometers, which is the same in-plane lattice constant between blue and orange. But this domain of the crystal should show the other spot to the opposite direction, which is positive 204 plus. But just coincidence. So this spot is overlapped with the substrate. That's why it looked like a 2 peaks, but in theory, so this is the 3 peaks, right, along the QZ direction. I confirms that with the different HKL condition. How about this spot here, 204 plus? So this is 180 degree rotated domain, which is green, and lattice parameter exactly the same as the orange. So in summary, so I found the crystal structure is monoclinic, A and B equal 0.387. C-axis is a little elongated, but beta angle is 0.5 degree off from the 90 degree. And every 90 degree rotation, so we have this domain, so 4 domains, right? Every 90 degree separated in the in-plane rotation direction. I have 5 minutes left. So this is my last talk today. So if you measure reciprocal space mapping, right, especially surface perpendicular direction 004, so you don't need to measure rocking curve because rocking curve is part of the RSM. So I just wanted to share with you how you can extract the rocking curve spectra from the reciprocal space mapping. So this is 004, the same data. So you simply need to extract the intensity distribution along the QX. This is the in-plane direction, right? Because in this area, the rocking curve direction is almost parallel to the QX. In the macroscopic view, the rocking curve has an arc. So that's why it's not really parallel to the QZ, sorry, the QX. But in this very small limited area, it's almost parallel. So it means you can extract the QX intensity distribution and you can do peak search. It was delta QX 0.004. But point is, so we need to know the degree of the peak broadening, right? So we are comfortable with the degree, but we are not comfortable with the reciprocal unit, right? I hope you agree. All right, so let's convert from delta QX to the angle. So peak with delta omega in degrees. So to do that, so very simple equation. So delta QX here should be divided by the QZ, which is 10.29 something. So then we got 0.02 degree. So this is the rocking curve peak width you're looking for. So you don't need to measure separated rocking curve if you measured reciprocal space mapping. Let's confirm. So I did rocking curve. Of course, I didn't have to, but I wanted to confirm for you. And I did rocking curve separately, but with a different receiving slit. So this is one of the information for you. So when you measure rocking curve on a thin film structure, so please keep in mind, so what you are measuring with the wider receiving slit is a convolution between delta QZ and delta QX. So let's go back to reciprocal space mapping. So delta QZ is a broadening along the QZ direction, this broadening. QX is this broadening. So if you have a very wide receiving slit, like a 1 millimeter, right, which is a default setting on our smart rough system, unfortunately. So 1 millimeter is broad, right, large. So what you get is a mixture between delta QZ and delta QX. And once you get this receiving slit narrower and narrower, so as you see, the peak is getting sharper. Of course, the intensity is compromised, but the peak is getting sharper. So what does this mean? So this is a plot, right? So receiving slit horizontal, peak width vertical direction. So if you get the receiving slit narrower, so the peak width is getting sharper. So at the saturated part around here, right? So we got 0.02 degree. So this is a delta QX, if you remember, right? So this is exactly the same information delta omega obtained, extracted from the reciprocal space mapping. So that suggests, so when you measure the rocking curve on the film, right? So we need to pay attention to receiving slit. So the receiving slit needs to be as small as possible if you are just interested in mosaicity. Otherwise, you are seeing the delta QZ. So by the way, why peak is broadened along the QZ? So this is because of the thickness. So diffraction peak is, I have 2 more minutes. So diffraction peak is a Fourier transformation of the electron density of the crystal. So the thin film has very limited thickness, right, along the Z direction, but very large along the in-plane direction. So if you Fourier transform this kind of shape of the crystal, so the peak is going to be like elongated along the Z thickness direction because of the limited thickness. Electron density is limited along the thickness direction. That is the reason why this peak broadening is caused. So means if you have a broad receiving slit, like a 0.8, so actually simply you are measuring the thickness of the film, not the mosaicity caused by the dislocation. So that's the point. So you need to reduce the receiving slit just to see the real peak width only caused by the dislocation or mosaicity. All right, so let me summarize my talk. So I think I have 1-2 minutes to receive to get your questions. So out of plane scan, so lattice mismatch. So this is different terminology compared to powder or polycrystalline film. Perpendicular from the sample surface, thickness from the thickness fringes can be analyzed. Reciprocal space mapping tells lattice mismatch both in plane, out of plane direction. And also you can determine crystal symmetry domain structure, like I demonstrated today. And also you can extract a rocking curve from the RSM measurement. So that's about my presentation today. Thank you for your attention.
All right. Thanks, Keisuke. So we have just a couple of minutes and we got some very good questions. So I'm going to try and pick just a couple to go, and then we'll have to direct the rest to after this session. So the first question we have that I was thinking would be a good one here is, does roughness affect penetration depth?
Very good question. Roughness affects the penetration depths. Yes and no. I mean, my answer will be yes. The first of all, we need to think about how the roughness is introduced, right? So the roughness is introduced by a roughened surface. So how the surface could be roughened? So one of the possible reason is, by introducing the dislocation. I'm looking for my schematic drawing, like I think I had, here, right? Yeah, so by introducing the dislocations at the interface with the large mismatch system. So this is actually the roughness, right, on the surface. So it means the roughness could be correlated, right, with the dislocation. So dislocation density matters. I mean, so the influence on the penetration depth, because depending on the crystallite size, the calculation, so how deeply penetrates X-ray might be modified because the total refraction angle is going to be affected by this roughened surface. So that's why it is influenced, but I cannot think of the exact equation which is connecting between roughness, amount of the roughness, and amount of the penetration depth, but it might be influenced by the surface roughness through the dislocations and the critical angle total refraction.
Okay, all right. All right, so we're going to do one more here, and hopefully this one we can get done too. Is grazing incidence or rotating better for measuring the thickness of an oxide on a rolled foil? So it's polycrystalline but has directional dependence, right? So it's an oriented film, oriented, right? So it has a orientation distribution function, I assume, due to the rolling direction.
Okay, very good. So if I understood, your sample is a foil, like a film structure, right? So the biggest challenge in your case is to make your sample surface flat. So as flat as possible, because if you try grazing incidence the scan, for example, like an in-plane scan like this, so the incident angle is going to be very, very small, like a less than 1 degree. So to determine such a small incident angle, if your sample surface like a random shape like a foil, it's almost impossible, right, to keep this incident angle constant. So this could be the first challenge. So if you can fix it, you fix your sample very flat. So I recommend GID if there is no preferred orientation, or in plane if there is any orientation of the field. But if your sample is difficult to be kept like a flat, so I think only way you could try is a symmetric 2 theta theta scan. This is out of plane. So it means X-ray hits the sample high angle theta, so which is not sensitive to the surface like a morphology, like a physical morphology, let's say.
Right. Okay. All right. So let's wrap this up. KSK, if you want to bring us back to the towards our end slides here. Yes. So that is all the time we have for questions. And as I said earlier, recording of the webinar will be available tomorrow. And an email will go out to all your registrants with instructions on how to view the recorded presentations. And I wanted to mention that we will answer all the questions again afterwards. And then we will also be hosting a second webinar, the final session of our practical XRD analysis with confidence series, focusing on X-ray, the different beyond diffraction and exploring nanostructure with SAX, wax, and X-ray reflectivity. That'll be on Wednesday, June 17th at 2 p.m. Eastern, 11 a.m. Pacific. And we thank you all for joining us, and we look forward to seeing you again in 2 weeks. Thank you, KSK. Thank you all for joining us.
Thank you, everybody. Thank you, Tom.
Thank you.
See you later.
Bye-bye.
Bye-bye.